Let's start chapter number 2, which is of vectors and equilibrium. Last time we talked about physical quantities, right? And we know that a physical quantity is defined as, you could say, it's a property of a matter that is connected with measurement, right? Now, a physical quantity itself, it may be a scalar quantity or a vector quantity. Now, scalar quantity may be defined as something that has a magnitude but no specific direction at all. So, hence, we say non directional quantity, while a vector quantity is something that has both magnitude and also a direction, hence, the term directional quantity. And so here are some of the examples of scalar quantities and some examples for vector quantities. So we know that to specify a volume, you don't need a direction, right? So you can specify the volume of an object by simply just a number, and hence it's a scalar, so it's just a magnitude. Similarly, for mass, you can specify a mass by just a number. You don't need to give it any direction. While for a vector quantity example such as velocity, you need to know if something is moving, that's fine. You can say that it has a magnitude of some number, but where is it moving, right? So you need to know what direction is it moving. In very simple terms, is it moving to the left or to the right? And similarly in vertical motion, if it's moving either upwards or is it moving downwards? Similarly, we have force, and you need to specify a direction to completely specify the variable force. And so similarly, you have for torque as well. Now let's very shortly discuss the scalar algebra versus the vector algebra. So the scalar algebra follows simple arithmetic rules such as your normal everyday addition, subtraction, multiplication, and division. While the vector algebra follows a set of special rules for your addition, multiplication, and division. Sometimes these symbols may represent those set of special rules, but it's not always the case. Also, you might notice there is no symbol for division over here, and that is because division is hopeless. Well, essentially, that just means that division is not achievable with vectors. Moving on to the modulus of a vector, it is simply the representation of your vector's magnitude, which means it is just the absolute numerical value of your vector, meaning that it is not going to give you any information regarding the direction whatsoever. For instance, suppose you are given two vectors. Vector A has a magnitude 5 newtons and it's to the north, while vector B has a magnitude of negative 5 newtons, which is to the south. So clearly vector A is not equal to the vector B, and note that I am using the word vector A and vector B, right? But what about the magnitudes of these vectors? What symbol should I put over here? Are they equal or are they not? So, well, we know what is the magnitude of this vector A. It's simply 5 newtons, right? And if you were to take the magnitude of your vector B, it would just eliminate the direction, which means it would eliminate this negative sign, which is telling you or giving you any information regarding the direction of this 5 newton. And so the magnitude of A is 5 newtons, and the magnitude of vector B will also be 5 newtons, which means that the sign over here should be an equal to sign, right? So the magnitude of vector A is equal to the magnitude of vector B, which is 5 newtons. Moving on, let's talk a bit about the behavior of our vectors. Starting with that a vector will not change if it is displaced parallel to itself in your space, then it will not change. And that is because if you look at these sets of two vectors, right? We have three sets of two vectors, and these are all parallel to each other. For example, the two vectors in this set are parallel to each other. Likewise, the two vectors in this set are parallel to each other, and the two vectors in this set are parallel to each other. So we see that these vectors which are parallel to each other, they are pointing in the same direction, even though you can see that this vector is over here and this vector is over here. And this is also one of the reasons that we can displace or put our vectors, just pick them up and put them somewhere else in space. But if they're pointing in the same direction and the magnitude does not change, then the vector remains the same, and so the vector will not change if it is displaced parallelly to itself in space. Secondly, if your vector is rotated through an angle theta such that theta is equal to 2n pi, right? And the condition over here is that the tail of the vector should be fixed, right? And so this n belongs to a set of integers, and so the n can take values from 1, 2, 3, 4, 5, 6, and so on. This is because the rotation of 2 pi radians is just a rotation of 360 degrees about a fixed point. And so if you look at this vector over here, if I rotate this vector with an angle 2 pi radians, so it will just come back to its original position, which is this, as you can see. And so I can do this any number of times, right? So I do a rotation one time, so it comes back to its original position. I do a rotation again, so it's n is equal to 2, so it will be 2 times 2 pi, so it will come back again to its original position. And similarly, I can do it any number of times, but because of this 2 pi, it will keep coming back to its same position, and hence the rotation of 2 pi n radians will make the vector invariant, right? So the vector remains invariant, that means it will not change. Moving on to when will a vector change, right? So a vector does change if there is any change observed in the magnitude, or if there is any change that is observed in its direction, or if both the direction and the magnitude change. Moving on to the angle between two vectors. This angle between the two vectors is measured when the tails or heads of these vectors are at one fixed mutual point. So suppose that these are your two vectors, vector A and vector B, and so this is the angle theta that would be measured as the angle between these two vectors. So you can see that these two vectors have their tails at a similar point. So both the tails start from this point over here, and so the angle between these two vectors is this angle theta. Now let's talk about the Cartesian coordinate system, which is also known as the rectangular coordinate system. And a Cartesian coordinate system in a plane is just a coordinate system which will specify each point uniquely by a pair of numerical coordinates. And we can discuss this coordinate system in different dimensions. So for our purposes, we'll talk about 2 dimensions and a 3-dimensional rectangular coordinate system. So we have, for a 2-dimensional system, we have x-axes and we have y-axes. And these axes are just your lines which are mutually intersecting perpendicularly to each other. And that one angle is enough to specify the direction of your vector that is represented in this 2-dimensional coordinate system. So you can see that this is an example of how your 2-dimensional coordinate system will look like. So you have x-axis over here and you have y-axis over here. Now it doesn't matter, you can decide which one do you want your x to be and which one do you want your y to be. And you can see that these are your lines, these axes are your lines, and they are perpendicular to each other. And if I have a vector in these lines, suppose that this is the vector, all I need is one of the angles to specify the direction. Suppose that that angle is your angle theta. Moving on to your three-dimensional rectangular coordinate system, which also consists of your x-axis, y-axis, but there's an additional axis, z-axis, which specifies the third direction, and these are also mutually perpendicular to each other. And to specify the angle in this case for a vector, you need three angles which will your vector make with x-axis, y-axis, and the z-axis. So now suppose that this is your coordinate system in 3 dimensions. So you have x-axis over here, y-axis is this one, and this is your z-axis, and you can clearly see that these are indeed mutually intersecting each other perpendicularly. And suppose this is your vector v in these in this coordinate system, and so these would be the angles that would specify the direction of this vector v. So you have theta x from x-axis, we have theta z from your z-axis to the vector, and then you have your theta y, which is from the y-axis to the vector v. Now let's talk about something that is called the head-to-tail rule for vectors. And this rule for vectors is used for the addition and the subtraction of your vectors. Now, so suppose we have your vector v1, which is this vector, and you have vector v2, which is this vector v2. Now, the rule or the point to be noted over here is that the tail of this vector v2 should be sitting on the head of vector v1, as you can see over here. And then if I were to draw a vector, so let's call it vr, such as a resultant vector, from the tail of your vector v1 to the head of your vector v2, then your vr is just the sum of your vectors v1 and v2. So this is also known as the graphical representation of your vector algebras, specifically your vector addition or subtraction. Now at this point, it would be a nice exercise for you to make a vector diagram in a similar way for the vector subtraction instead of the vector addition. Moving on, let's talk about the resolution of a vector, or how do we resolve a vector. So when you resolve your vector, what you get is what is called the components of that vector. So that means that if you are resolving your vector, then you're obtaining the components of that specific vector. Now these components that you get after resolving a vector, they must be mutually perpendicular, right? So well, giving you an idea, suppose that this is your coordinate system x, y axes, and you have a vector in this coordinate system, vector v. So the resolution of this vector into its component will look something like this, right? So we have its horizontal component, also known as the x component of your vector v, and you have the y component of your vector v. So what these resolution of these components is only telling you about how much of this vector v is pointing or is along the x axis and how much of it is along the y axis. So that's what y component will tell you. Now these components can be easily written down by using very simple geometry. By the way, we can even write down our components for vector v as vx. This corresponds to the x component of your vector, and vy, which corresponds to the y component of your vector v. Note that there is no vector symbol on this vector on this component vx, and the reason for that is that this is not a vector, but it is the component of your vector v. So it only has this x direction, and therefore it is only giving you information about how much of this vector v is in the x direction. So by borrowing trigonometry from mathematics, we can write down these components Vx as V cos theta and Vy as V sin theta. And you can see that clearly that the direction of these components is simply contained in this angle theta. Now, just for the fun of it, let's see what happens if I square these components individually. So I square Vx and I square Vy and then add those two together. What do we get? So we have Vx squared and we have Vy squared, and we know that Vx squared is, so this would become V squared cos squared theta plus V squared sin squared theta. But you can clearly see that from this expression we can factor out our v squared, so we get this expression over here. But from again trigonometry, we know what is cos squared theta plus sin squared theta. It is just a unit, right? It is just 1, which means that this is just v squared. But what is v squared? V squared is simply the magnitude of your vector v squared, from which we can establish that the magnitude of the vector v is given by the square root of the sum squared of its components, which is vx squared plus vy squared. And in the similar way, you can do this Vx component divided by Vy component. Note that these are the components of the vectors, and so I can perform this division as these are not the vectors themselves. And so the division of these two components will lead to this expression for theta. So you can determine the angle between these two vectors as the tan inverse of these components Vy over Vx, right? So this would be a fun exercise for you to try out. Now, moving on, let's quickly talk about the scalar product, which is also known as the dot product. The name given dot product is because of the symbol, and it is written as the dot product of vector A with the product of vector B, and it's called scalar because this is going to give you a number that is A times B times cosine of theta, which is just a number. So it's a scalar. So we see that if I take two vectors and if I multiply them with this dot, or in this way AB cos theta, then this just gives you a number. So that number is called a scalar. A very famous example for a scalar product is work, right? How? Well, what do we know about work? We know that it is simply force times distance, but we have a dot product over here, and this dot product is telling you that the multiplication of force and distance is such that in whatever direction I have the force applied, and then the object moves a distance d in that same direction where the force was applied, then this will give you some value which would be the work done, and hence the work done would be non-zero in this case. So this is the situation that I'm talking about. So you have a block over here and you exert some force on this block to push it to the right side, and suppose that it moves some distance d to the right with this amount of force acting on this block. So this distance is a vector quantity, as this is the direction is to the right side, and so we take this force vector and we take this d vector, distance vector, and we take the dot product of these two, so it returns you a number, which number is for computed if the force and the distance d are pointing in the same direction, and it's called the work done in moving this block to the right distance d. Let's quickly go through some properties of the scalar product. So the scalar product is commutative, which means that if I take the two vectors and multiply them this way, a dot b, it would be the same thing as if I take the vector b and take the dot product of vector b with vector a. So these two things are exactly the same. So they obey, the scalar product obeys a commutative law. They also follow associativity, such that if I have a vector a and I scale it with some number m, and I take the dot product of that thing with a vector b which is also scaled with some number n, it is the same if I take the product of these two scaling factors m and n and then multiply the entire thing with the dot product of vector a and b. So these two things are exactly the same. And for unit vectors, we have the following property, such that if I have a unit vector I and I take a dot product with the same unit vector, then I'd get 1, right? So if I take the same unit vectors, you can see over here, you'd get a unit 1. But what about if I take unit vector I and I dot it with some other unit vector? Note that these two vectors are perpendicular to each other, I and j, and likewise k and j, and so on. So if I take two different orthogonal or perpendicular vectors, then the scalar product of those would be 0. And likewise, and if I take the unit vectors which are exactly the same and I take the dot product of those two, it will give me 1. And finally, we have the angle between the two vectors a and b, which are to be scalar product. It is given by the cos inverse of these components. So I have ai and bj multiplied, and then you see this weird symbol, it is known as the summation, and so you would have ax bx plus ay by plus az bz divided by ab. Next, let's discuss what is called the vector product. It is also known as the cross product. So suppose I have two vectors a and b, and the product of these two vectors is going to return a vector, then this product between these two vectors is known as the vector product. And over here we have n unit vector, and this unit vector is simply normal to the plane that contains these vectors a and b. Now let's go over a few of the properties for the vector product. So the first one, we have that if I have a vector a crossed with vector b, and suppose then you have another thing that is vector b crossed with vector a, these two things are not equal whatsoever, right? So that means that there is no commutativity between these two. Next, suppose that if I have two vectors which are exactly the same and I cross those two vectors, that would just give me 0, right? So the cross product of same vectors vanishes, right? Next, we have vectors a and b, and suppose that these vectors a and b are perpendicular to each other, so that the angle between these two vectors is 90 degrees, then the result is simply a b n hat, because sine of 90 degrees is 1. Next, we have this thing which is also sometimes called as a cyclic rule for unit vectors. So suppose that if I were to take a cross product of I and j, that means I have to go in this direction, right, to move from I to j. And so we see on this circle the direction is pointing exactly where I want to go. So that means that if I were to go from I to j, I cross j, and if I keep going, that would give me positive k. And suppose that if I were to do it the other way around, so let's say I wanted j cross I, so what would that be? Well, I would have to go in this direction, which is opposite to the direction that is indicated on this circle. So going from j to I, which means if I were to go here, then I encounter this direction, which is opposite to the direction where I want to go. So I would add a negative sign with this k, right? And so that's how you can compute all the cross products of your unit vectors I, j, and k with each other. So now finally, suppose that if I were given two vectors A and vector B and I were to compute this cross product, how would I do it? Well, we have this trick where you take the determinant of something like this, where you have the x component of vector A under this I hat, and you have y component of vector A under j hat, and you would have z component of vector A under k hat, and likewise you would do for vector B, and then you would simply compute the determinant of these vectors, and whatever answer that you get, you would have these I, j, and k with it, right? So you would have I, j, and k with it. And so whatever answer that you get, it is the result of this A cross B, which would be some other vector, let's call it V. And that's how you'd compute the cross product of these two vectors. So let's conclude this lecture over here, and let's make a part 2 of this, where we'll talk about some of the physical quantities such as a torque, and we'll also define the equilibrium and a complete equilibrium, where we'll discuss the conditions for equilibrium and so on.